Imagine paying someone $71,337 basically, just because
Why?
they figure out how to hijack a billion Android devices.
Yeah.
And, doing it using a window of time that lasts exactly 6 CPU instructions.
Right. Yeah, it's wild. No power drills, no like massive malware payloads dropped onto a hard drive or anything like that.
Exactly. Just this microscopic phantom doorway in the operating system. It opens and closes in a fraction of a millisecond. If you hit it perfectly, you own the machine. And if you miss, well, nobody even knows you were there.
It really just completely upends how we traditionally think about perimeter defense. We spend all this time building these taller and taller walls. But when the foundational concrete of the system can be tricked into, well, briefly ceasing to exist, the wall itself just doesn't matter anymore.
Yeah, and that vanishing doorway is the absolute reality of the zero-day vulnerability we are digging into today. So welcome to the deep dive. We've got this, frankly, terrifying report to unpack from Cybersecurity News.
Written by Guru Baran, right?
Yeah. Yep. Guru Barana. And it details this fundamental flaw in the Linux kernel that researchers have dubbed bad EPL. Formally, it's tracked as CVE 2026-46242.
And, the stakes here are absolute. Bad EPL allows an unprivileged local user to escalate their permissions directly to root. Total system takeover.
Wow.
Yeah, and that applies to Linux servers powering the internet, enterprise desktop environments, and, critically, for a lot of you listening, the Android phone sitting on your desk right now.
Master keys to the kingdom, just handed over by a glitch measured in nanoseconds. So our mission today is to figure out the mechanics of this break-in. We're going to explore how an attacker actually forces that tiny window open, why Anthropic's state-of-the-art Mythos AI completely missed it during a code audit, and why, for your servers and devices, there's just no temporary workaround.
Right, you can't just flip a switch to stay safe here, which makes this a total masterclass in how fragile fundamental infrastructure can be. But, to really grasp what's happening, we have to look at the engine of the operating system itself.
Okay, let's unpack this at the foundation then. I know OBL is short for event pool, right?
Right.
In the Linux kernel, it's basically the air traffic controller for data streams.
Yeah, that's a really good way to visualize it.
So it tells the system when a file or network socket or a pipe is ready to be read from or written to.
Exactly. It manages just massive, massive amounts of concurrent connections. And to do that efficiently, it has to be incredibly precise about how it creates and destroys the data structures tracking those connections.
Right.
So the root cause of bad EPL is a failure in that teardown process. It's a specific mix of a race condition and what we call a use after free vulnerability.
Okay, so when a connection is finished, the air traffic controller needs to clear the runway, basically. How does that process actually fail?
Well, it fails because of how it manages its internal locks. When an object is no longer being watched by EPL, the system starts its cleanup routine. It puts a lock on the file to say to the rest of the kernel, like, hey, I'm working here, don't touch this.
Right, like a do not disturb sign.
Exactly. And under that protection, it clears out the directory pointer. But then it makes this fatal mistake. It drops that lock just a fraction of a second before it finishes wiping the rest of the file's data from the active memory list.
So it takes down the do not disturb sign while it's still packing up its bags inside the room.
Precisely. And in a modern processor, handling billions of operations a second, taking down that sign early creates a race condition.
So if someone else walks in.
Right. If a totally separate process comes along at that exact microsecond, like a concurrent call looking for that file, it sees that the directory pointer is empty. It just assumes the teardown is completely finished.
Even though the first process is still actively working in that memory space?
Right.
That is wild.
Yeah, so the second process says, great, I'll skip the normal safe release routine and just force free the memory structure right now. It yanks the rug out from under the original cleanup process.
And so the original process is now holding on to and trying to use memory that the system thinks is completely empty and available.
Exactly. That is your use after free.
So it's almost like a coat check where the attendant hands your jacket away to someone else, but you're still holding the ticket. You reach in to grab your keys from the pocket, but you end up rummaging through a total stranger's belongings.
That is a perfect analogy, yeah.
But this isn't just a standard use after free, right?
Yeah.
Because EPL uses a very specific type of memory management. RCU, is it? Read, copy, update.
It does, yes. And this is where the vulnerability turns from just a kernel crash into a devastating weapon. The kernel doesn't just destroy the physical memory space immediately when something is freed.
Okay, why not?
Well, for performance reasons, mostly. Under RCU, it keeps that physical slot available in a cache so it can be recycled instantly by a new process.
So it's like tearing down a condemned bank branch, but instantly handing the same physical address over to, I don't know, a fireworks store, while the old bank manager still has the front door key and thinks he's walking into his vault.
That is exactly it. The system allocator recycles that exact memory slot for a completely new, empty file structure. And then the original confused process executes a memory-freeing command against what it thinks is the old structure, but it's actually deleting a vital, active component of the new memory cache. It's blindly firing a demolition order into the kernel's memory management system.
Okay, wow. I track the mechanics. The system leaves this phantom doorway open because it dropped a lock too early. But wait timing that concurrent call perfectly sounds like trying to catch a bullet. How wide is this window of opportunity?
That's probably the most staggering part of the report. The race window is almost incomprehensibly small. We're talking about roughly 6 CPU instructions.
6 instructions. Are you kidding? That isn't even a rounding error in processor time. I mean, how does a human hacker guarantee they hit a window that tiny? You can't just throw millions of requests at it and hope you get lucky without crashing the entire server, right?
Right. You definitely can't rely on luck. You have to engineer the environment to basically bend time in your favor. And that brings us to the security researcher, Jae-young Chung. He didn't just write some academic paper theorizing this was possible. He built a fully functional zero-day exploit, submitted it to Google's highly competitive Kernel CTF program, and proved it could be weaponized reliably.
Here's where it gets really interesting. That's the exploit that earned him that $71,000 bounty. So how did he guarantee the timing?
He used a classic setup and knockdown strategy, but executed it with just surgical precision. Chung grouped 4 different EPEL objects and split them into 2 pairs.
Okay.
By intentionally closing one pair, he triggers the exact cleanup routine we just discussed. He forces the kernel into that microscopic window of vulnerability. Meanwhile, the second pair serves as the victim object.
So he's essentially creating like a highly controlled traffic jam in the kernel to slow down the exact process he wants to exploit.
Exactly. He's manipulating the CPU scheduler to widen that 6 instruction window just enough to slide his concurrent call in. But, hitting the window is only step 1.
Wait, there's more.
Oh yeah. The initial use after free only gives the attacker a tiny 8-byte write primitive. 8 bytes of memory corruption isn't really enough to take over a system.
So how on earth do you turn 8 bytes into full root access?
Through a cross-cache attack. See, the Linux kernel organizes memory into different sized slabs, almost like specialized warehouse shelves. Some shells hold harmless networking data, while others hold critical security credentials.
Right.
Chung figured out how to use that tiny 8-byte write to break the divider between the shelves. He forces the kernel to mistake a less important memory pool for a massive critical one.
Oh, wow. Tricking the allocator itself. So he's taking a localized memory error and using it to basically overwrite the core operating instructions of the machine.
Yes, and because of the traffic jam he engineered, he doesn't just hit the window once and cross his fingers. He designed the exploit so he can retry the attack over and over without triggering a kernel panic.
Really? How reliable is it?
He achieved an astonishing 99% reliability across his test targets.
99%. I mean, so if an attacker runs this script against your infrastructure, it practically never misses. And once they cross that cache boundary, what are they actually doing with that access?
They establish an arbitrary read primitive. Essentially, they gain the ability to silently read any part of the kernel memory.
Yeah.
They do this by manipulating a specific file path, the /proc/self/ of dinfo path.
Which normally does what?
Normally, it just outputs harmless data about open files. But Chung corrupted the structure so that querying that file acts as a periscope, allowing him to read the raw, secure memory layout of the entire operating system.
It's like a magic pair of X-ray glasses. You can see exactly where the security guards are standing inside the vault.
Precisely. And once you can see the layout, you hijack the control flow.
So they aren't even writing new malicious code into the kernel. They're just calling off a classic ROP chain, right?
Yeah.
Return-oriented programming.
Yeah, that's it.
So they just cut tiny snippets of legitimate kernel code that already exist in memory and string them together like a ransom note to execute malicious commands.
Which ultimately spawns a root shell. Complete administrative control. But Here is the detail that truly escalates this from a server problem to an endpoint catastrophe. This exploit is fully reachable from inside Chrome's renderer sandbox.
Wait, hold on. I thought the whole point of Chrome's sandbox was that it was hermetically sealed from the kernel. I mean, it uses strict system call filtering to ensure malicious JavaScript can't touch the underlying operating system.
Right, that's the theory.
So how is a memory bug in the OS reachable from inside a web browser?
It really comes down to functionality.
Hmm.
The sandbox restricts most system calls, sure, but a web browser fundamentally needs to communicate with the network, And to do that efficiently, the sandbox has to allow access to the ePOL subsystem. It's an authorized pathway.
Oh, wow. So they just walk right through the front door.
Basically, yeah. Normally, to hack a machine through a browser, an attacker needs a chain of complex bugs. One to execute code inside the browser's JavaScript engine, and then a completely separate, highly sophisticated sandbox escape to break out into the OS.
But because Bad Apple is already allowed.
Right, because it sits on an authorized pathway, an attacker who already has a browser exploit can chain it directly to Bad Apple. They bypass the sandbox isolation entirely, achieving full kernel takeover simply because a user visited a maliciously crafted web page.
It's just driving me crazy to think about the level of human intuition required to pull this off. You have to perfectly engineer this synchronized ballet of memory manipulation, cross-cache trickery, and RCU timing just to exploit a 6-instruction window.
It's a work of art in a terrifying way.
Which forces the question, like, where did this bug come from? And why didn't our massive automated code scanners catch it before it was shipped to a billion devices?
What's fascinating here is the origin story. This wasn't some legacy flaw that sat dormant in the kernel for 2 decades. Both bad EPOL and a related bug were introduced very recently.
How recently?
They were pushed in a single kernel commit in 2023.
So someone submitted a patch to optimize the code and accidentally planted 2 separate race conditions right next to each other in the exact same 2,500-line code path of the EPOL subsystem.
Correct. Now, the first of those 2 bugs, tracked as CVE 2026-43U074, made major headlines recently because it was discovered entirely by an AI. Specifically Anthropic's frontier AI model, Mythos.
I remember that. The industry celebrated it as a massive milestone. It proved that large language models were finally capable of understanding and finding complex kernel-level race conditions.
Right, it was a big deal.
But wait, that raises a glaring red flag.
Yeah.
If Anthropic's AI audited this exact code path and found the first bug, why on earth did it completely miss bad EPOL sitting right next to it? Is it because AI just can't conceptualize microscopic timing windows?
Well, it's less about the timing window itself and more about how AI models actually learn to hunt for vulnerabilities in the first place. It highlights a really critical limitation in current automated security.
Okay, lay it on me.
AI models like Mythos are incredibly good at pattern recognition, right? But their training relies heavily on observable failures.
Meaning they need to see a crash log to know something went wrong.
Exactly. The Linux kernel uses a robust tool called Kazan, the kernel address sanitizer. It's the primary memory error detector.
Okay.
Think of it as a die pack exploding in a bank vault. If a process tries to access memory it shouldn't, Kazan catches the violation, triggers a massive warning log, and provides a forensic trail. AI models train on those Kazan logs. They learn what the die looks like.
But bad EPOL doesn't trigger the die pack.
It almost never does, because the race window is so small, and crucially because it abuses those RCU memory caches that recycle instantly, the corruption happens silently beneath the sanitizer's radar.
Wow.
Yeah, the memory is formally marked as valid by the RCU system, even though it's logically corrupted.
So to Kazan and to the AI looking at the logs, everything looks perfectly normal.
Yep. There is almost zero runtime evidence left behind. It is practically an invisible bug. An AI scanning the code logic or running fuzzing tests doesn't see a crash, so it just assumes the code is safe.
And so it required a human researcher relying on deep systemic intuition about how these highly abstracted memory systems interact in the real world to spot the theoretical flaw and engineer the environment to exploit it.
Exactly. Humans can intuit the invisible gaps.
So what does this all mean for your servers or, the Android phone in your pocket right now? We've got an invisible bug that easily evades AI detection, weaponized with 99% reliability by human hackers, granting total root access.
Yeah, it's a perfect storm.
Right. And when a nightmare bug like this drops, IT teams usually scramble to apply a temporary mitigation while they wait for a formal patch, right?
Usually, yes. Like, if we look at the copy fail bug that caused chaos a few months ago, that vulnerability existed in optional kernel modules.
Oh, I see.
So if you were worried about being exploited, your system administrator could just go into the configuration, disable those specific modules, and basically neutralize the threat. You might lose some peripheral functionality, sure, but your core system remains safe.
Like a surgical amputation to stop the
Yeah.
infection.
Yeah, but you absolutely cannot do that with bad ePOL. As we established earlier, ePOL is the foundational event notification facility for Linux.
Right.
If we connect this to the bigger picture, it is the beating heart of the operating system's networking and file management.
So you can't turn off the air traffic control tower without grounding every single plane in the sky.
Exactly. You cannot disable it, and you cannot unload it from the kernel without completely bricking the operating system and breaking all modern browser functionality.
So there's no stopgap.
None. Which means there is no temporary workaround. You can't tweak a firewall rule or change a configuration file to make this go away. Administrators and end users are entirely at the mercy of the upstream patch.
And according to the Cybersecurity News Report, that upstream patching process was anything but smooth.
Oh, it was a disaster. When the vulnerability was first disclosed, the maintainers of the Linux kernel obviously rushed to implement a fix. But because the interactions between the teardown locks, the RCU caches, and the cross-cache attack vectors are so incredibly convoluted, their initial patch didn't actually resolve the issue.
They patched the symptom, basically, but left the microscopic doorway open.
Right. It took nearly 2 months after the initial disclosure for a truly correct, comprehensive fix to land in the mainline kernel.
2 months. That is a massive window where billions of systems were sitting entirely vulnerable, with no mitigation available, completely exposed to anyone who could reverse engineer Chung's methodology.
It really is. And even now that a correct patch exists in the main Linux repository, that doesn't mean your phone is magically safe today.
Because of the supply chain.
Exactly. That's the brutal reality of the software supply chain. The fix exists upstream, but now every single distribution like Ubuntu, Red Hat, Amazon Web Services, they all have to backport that patch into their specific kernel versions.
And for Android, it's probably even worse, right?
Oh, much worse. The patch has to flow from the Linux kernel to Google's Android open source project, then down to device manufacturers like Samsung or Motorola, and finally to your specific carrier before it actually hits your device.
A process that can easily take 6 months to a year. And that's assuming the manufacturer still supports your device at all.
Which leaves this ocean of devices permanently vulnerable to a highly reliable, completely invisible root exploit.
Well, it's just a stark reminder of our absolute dependence on these deep foundational layers of code, you know. We went looking for a vanishing vault door today, and we found one terrifyingly well hidden.
We really did.
We unpacked a microscopic 6-instruction race condition buried in the core networking component of Linux. We explored how human ingenuity weaponized that tiny window-creating kernel traffic jams and tricking the memory allocator to bypass the Chrome sandbox entirely.
Yeah.
We saw how this silent memory corruption completely blinded state-of-the-art AI code scanners. And finally, we learned that because eVPOL is the beating heart of the OS, there are 0 temporary workarounds. It proves that keeping your infrastructure and your personal devices relentlessly updated isn't just best practice, you know. When dealing with core 0 days like bad ePOL, patching is literally your only line of defense.
It is the only way to close the door. But,
Yeah.
as we look at the broader implications of this deep dive, there is a distinctly unsettling trend emerging here.
What's that?
Well, we noted that Anthropic's Mythos AI successfully found the first bug in that 2023 commit, the noisy bug that tripped the memory sanitizers. As these frontier AI models become universally deployed across software development, they are going to rapidly sweep up and eliminate all of those standard, traceable vulnerabilities.
They're going to automate the discovery of all the low-hanging fruit. The die packs will catch everything that makes a sound.
Exactly. Which leaves us with a really provocative question for you to mull over. If AI patches all the visible cracks in the vault, will human hackers simply give up? Or will they be forced to adapt, exclusively hunting in these silent, invisible 6-instruction shadows where the AI cannot see?
Yeah.
Are we entering an era where human threat actors become ghosts, specifically evolving their entire methodology to exploit the blind spots of artificial intelligence?
A chilling thought to leave you with. The vault door might be invisible, but the ghosts figuring out how to walk right through it are very, very real. Thanks for joining us, and we'll catch you on the next deep dive.